Can we start?
Yes, Pramod.
Good afternoon, good evening to all. My name is Pankaj Amin, President, Ashray Bahrain Chapter, MP Chair for year 2021. On behalf of Ashray Bahrain Chapter and BOG, I welcome all Ashray members and other participants representing HVAC field covering the design, engineering, sales, production, construction, facility and energy management. Ashray Bahrain will conduct more technical webinars on our own webinar platform as well as jointly with the regional chapters. Special thanks and welcome to our technical presenter today, Mr. Raj Mohan from Armstrong, to deliver the technical presentation on smart pumping for maximum efficiency and cost saving in collaboration with Ashray Bahrain chapter. Now I will invite Mr. Desi, our CTCC and Sustainability Chair and past president, to brief about Ashray and introduce our today's speaker. Over to Desi, please.
Thank you, Mr. Pankaj, and good evening to you all. And thank you for joining in for today's event. As Mr. Pankaj has said, we have started our new society year with a new board of governors, and today is the first of the many seminars planned by the new board. Before we start on, I would like to give you a small brief on the Ashray as a society and its activities over the world. As of now, Ashray has about 57,000 members in over 132 countries. The membership base is from various sections of the HVAC industry, from manufacturers to consultants, academias, the contractors, and the students. The vision and the mission is focused on creating healthy and sustainable spaces to serve humanity. Also, Ashray is celebrating its 150th year of inception, which makes it among the oldest organization in the industry. This is a code of ethics, and I quote, "In this and all the Ashray meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for all the others, which exemplify our core value of excellence, commitment, integrity, collaboration, volunteerism, and diversity. We shall avoid all real or perceived conflict of interest." On the society level, this is the Ashray's new executive committee, which comprises of Mr. Charles Gullich, who is the society president, Mr. Michael Swidler, who is the president-elect for this year, and Mr. Farooq Mahmood, who is the treasurer. And then we have the vice presidents. Mr. Farooq, he is the first of the people from this society to be taking up the responsibility at the society level. This year's Ashray's theme is the Digital Lighthouse and Industry 4.0. This is basically that our industry is one of the least digitalized industries in the entire sector. And as per the McKinsey's, one of the McKinsey's report on the digitalization data, we rank lower than the industries such as agriculture and hunting. And the second issue is the integrated process, though it has been discussed for some time now, but it is not actually being implemented. So this year's theme basically tries to promote the integrated design process and digitalization. And if you'd like to know more about the topic, you can go to ashray.org for the presidential address. Just to take you around the Ashray's activities, Ashray basically operates around the world, and it is divided into 15 regions. The largest of the region is the region at large, which is basically the Middle East and India, where it falls into. And it is one of the largest with about 30 chapters. And these are the board of members, board of directors, and Mr. Ala, who is our DRC, who you can see in the top right corner of the frame, and he is heading the region at large. Mr. Ala, he is supported by two regional sub-region chairs, and Mr. Richard and Mr. Akash, and Mr. Richi Mittu is the regional membership council committee. And basically, region 1 covers the Middle East and Africa, while region 2 covers the Indian subcontinent region. Here, I would also like to make a mention of that our past president, Mr. Adil Imam, who had been who has been appointed as the RVC of the membership promotion, and thus he has started parents representation in the RAL this year. This is a research promotion is something which ASHRAE requires for its own purpose of research, and as our commitment to this organization, this is something which we should see that we can do that, and if anybody is interested, they can let us know. Again, membership is the key to all our success. So if anybody is interested to get the membership, they can contact us and we can help them in getting it. Now, because of the COVID situation, most of the courses are going online, and there are few courses which are already arranged at the Global Training Center. And I would request all of you to take advantage of that because it is at a much discounted rates, and it's quite beneficial to everybody. Now coming to Bahrain chapter, as we said, we have started the operation under the leadership of Mr. Pankaj Amin as the president and Mr. Mohammad Farhan as the president-elect. And Mr. Kiran Kumar and Mr. Dhruv Kumar and Mr. Shahbaz, they have joined as a new board members for this year. Our membership has seen some increase in the past few months. Already 7 people have been, we have 7 new members who have joined the ASHRAE group, and more are expected to join soon. Mr. Shahbaz, Ms. Fatima, Mr. Hussein, Mr. Prajesh, Mr. Pradeep, and Mr. Abdul Kalam, and Mr. Mohammad Saeed. And we thank you all for your support. And coming to today's webinar, it is titled Smart Pumping for Maximum Efficiency and Cost Saving. To present this, we have Mr. Raj Mohan Govind from Armstrong Fuel Technology. He leads the team of building service system and solution for Armstrong Fuel Technology for Middle East and Africa. He has contributed to the field of HVAC and plumbing for the last 16 years. Before I hand over to him, I would like to request you that in case of any questions, please feel free to type it on the chat box. Your questions will be compiled and Mr. Rajmohan will try to answer as much as the time permits. Also, please note that there will be a feedback form at the end of this webinar. Please fill it so that we can have the necessary feedback from you. So now please join me in welcoming Mr. Rajmohan for the presentation. Over to you, Mr. Rajmohan.
Yes, Rajmohan.
Yeah, good evening and welcome all to today's learning session on smart pumping for maximum efficiency and cost savings. Let's look at the agenda for today. Overview of today's HVAC pumping. We look at what's latest today, cloud-based optimization and latest technology. Censored versus sensorless smart pump controls. Pump selection for HVAC applications, both constant flow applications and variable flow applications. Types of pump controls, multiple pump installations, and staging of multiple pumps in parallel. On the left, we have the traditional pumping systems and how we use those for today's applications. So to start with, today, to look at energy optimization decisions or performance decisions, asset management, we need data from the from any device that or asset that we have in a building. But with the traditional pumps and controls, we have very low information that will aid in complete active performance management. Whereas we have smart pumping controls today, which can connect to cloud, optimize by machine learning. So there comes an opportunity with smart pumping. Traditionally, we used to have pressure sensors installed in the building pipes. We used to have our own challenges in installation, performance drift, reliability of the sensors, etc. Now, with sensorless or smart pump controls, you can overcome those challenges and use smart controls, which is embedded on the pump controls itself. We used to have excessive redundancy. Even if you take a 2-year-old installation today, redundancy is looked at differently. We'll talk about that in the coming slides. So excessive redundancy is something which we see in the industry, but we do have a big opportunity in appropriately sizing pumps and having the right redundancy in parallel application. Another challenge is oversized pumps, motors, and when you oversize pumps and motors, the variable speed drives are also to be selected for those big motors. So, so the full potential of variable speed is not being used while we take that approach. But today's smart pumps allow you to select the right sized equipment and reduce installation costs. When we say smart pumping, it's a holistic approach to the whole process, right from the system design, selection, and right sizing equipment, and then using smart controls and continuing that to manage the performance over time. It's just not over once you commission it, but you'll have to have a sustained performance over time. So that's what we call it as smart. Smart should be low on installation cost, and smart should be providing less operating cost over time. Today, like any other equipment, the pumps have smart pumps have Wi-Fi capability. They can connect to cloud, and it can aid or activate active performance management. So what is performance management? You will have analytics and pump specific insights, just not information like the kilowatt or the voltage or the amperage, but it should tell you specific insights on that particular pump operation. It should provide insights that reduce operating cost and that actually tells you that the predictive maintenance aspects of it. So by doing that, it enhances the reliability and sustained optimal performance is achieved. Now, looking at traditional pressure sensors, how or where it can be placed. Today, we walk into the mechanical room, we find the sensors installed in the plant room most of the time, which is number 1 at the bottom, just close to the pumps, just because it's easy to install in the plant room. The second place and the best practice as per ASHRAE recommendation is remote load, or 2/3 of the farthest loop. Now that's the best practice, but it's often seen as a difficult place to install, and more often we see the sensors going into the plant room. Now that could be another sensitive load in that building. It could be a server room, or instead of putting in a remote zone, probably they have a high pressure pressure drop area, and we want to put the sensors in that particular location as well. So these are possible sensor location placements, and let's look at what it does to the energy performance when it placed in the most popular mechanical room location. So when you actually put the sensor out there, you got to maintain a minimum head which is very high, which means your set point is high. So the control curve looks almost flat. The operating curve, or the red curve, what you see here, looks almost flat. Now you could do a slightly low set point to optimize, but it's still going to be little reduction in speed, achieving some amount of energy savings, but it's not the best. It's easy to install, but it's not the best in energy performance. Now coming to the sensor at remote load, you install the sensor in the remote air handling unit, or the shaft, or the farthest riser. Now you got a smallest set point because it's farthest and the farthest loop. Now this provides an opportunity to set low set point, a low minimum head that we are showing here, the point B. Now the point B connects to the design day flow and head, which is the maximum load that we have designed for. Now once we do this, the operating curve is much quadratic, and you have a larger energy savings opportunity because you can slow down that pump now to a much lower speed and still meet the demand of the building. So some of the challenges that we face today in placing that sensor in the right place, we have challenges in selecting the differential pressure sensor for the right range. Often we see in the field that you need a set point of let's say one bar or less, and differential pressure sensors are selected for 0 to 6 bar, and hence the readings that the differential pressure sensor sends back is very inaccurate, and often there is a cost involved in replacing to the right sensor when it comes to the execution. It also is a cost to install wiring and install that wiring in a separate conduit than the power wiring, and avoid the interferences and any sort of damage to those wiring. And then where to place the sensor, how much should be the set point is another discussion that goes on in the industry. Calibration is a challenge. Once you install, commission, often sensors are not calibrated. That's been a challenge in many operation maintenance teams in the buildings. So they are prone to drift over time, whether it be scaling, air loss, or some other sort of damages. Pre-programmed mapped and tested factory configuration can bring benefits and avoid all of these risks and challenges associated with the sensor and its installation. You don't need to do any custom programming from the BMS or controls contractor end. Once you have an integrated embedded control on a smart pump, it will take away the risk of all above items. Now that's why you will have lower installed cost or initial cost even by having a smart pump. So it has to be looked at as a holistic approach to the cost reduction to the project rather than equipment to equipment. Now coming to the traditional way of control and how a sensorless control works. Just an overview. So on to the left, the censored system, which is DP sensor. We talked about the locations. So the DP sensor reads the value and sends a signal back to the variable speed controller in 4 to 20 milliamps signal. So this 4 to 20 milliamps is read by the variable speed drive, and the variable speed drive modulates the speed to achieve the provided set point. Now coming to sensorless control, it changes whenever there is a change in the system behavior or demand. The first thing that senses the change in pressure or flow requirement in the building is the pump, because it's a closed circuit, and as we know from pump affinity law, pressure flow changes, amperage changes. So once you have embedded program maps inside the controller of the pump, it becomes smart, and it can, by reading amperage from the inbuilt control sensors, it can go into the map and provide you the actual operating point and sense the demand of the building. And when the demand drops, the pump slows down. When the demand goes high, the pump speeds up. So it's a simple overview of how a smart pump would work, sensorless. Now let's discuss the applications with the HVAC industry. So first is a constant flow application, circulation requirement. So if we talk about a constant primary system, chilled water or hot water, we can also talk about condenser water. It's also constant volume most of the time. Now when it comes to constant speed or constant flow, traditionally we used to trim impellers to actually suit to the actual operating point on site. And then when the variable speed controls came, we started reducing the speed and measuring the flow at the time of commissioning, which needs a flow meter. And we started achieving the flow at reduced speed. Now this is rare cases. Most of the time we don't see variable speed drives on constant volume pumps, as it's seen as a high investment and no energy savings, because nobody has the logic to actually control the variation in flow, or we don't want to control the variation in flow. So the energy saving opportunity is not looked at often. Now, what is best practice? When you have a smart pump sensorless control, you could program a flow rate, or you could program a particular pressure, and you could let the pump maintain that particular flow. by doing that, even if somebody adjusts any valves over time or any scaling happens in the, for example, in a condenser, the flow rate tends to drop when you put it in a certain frequency, because we don't know the flow rate. We are not actually measuring the flow rate on the traditional pump control. But in best practices, when you know flow directly and you program the flow, the smart pumps can actually maintain the right flow required to the equipment, and thereby just not save energy on pumps, but it will also save energy on larger piece of equipment like chillers, because it maintains the required flow rate, and thereby the chiller is more efficient in operation all the time. Now that's for constant flow applications. Talking about variable flow applications, such as secondary or a variable primary or a hot water application, it's a sensor system, be it a differential pressure sensor or temperature sensors. This is censored PID loop control that is being practiced in the industry. And the best practice is again sensorless because of all the risk of risks associated with the sensors, the sensor placement, and the set points and the drift that we talked about. Now, when you have this type of control here, sensorless control, you can easily change and simulate the different location of sensor or different set point for the sensors. Now that will give a greater flexibility to recommission your system even if something changes in the system. For example, the building is occupied for, let's say, 5 floors, and the client decides to build another floor on top of it, or let's say the last floor was not occupied and now it's getting occupied. When something changes in the system, flow requirement also changes, which means your sensor placement also should be changing. But with the smart pumps, you can actually simulate that control curve that is equivalent to replacement of the sensor, so the new sensor position. You can also change set points very easily from the smart pump interfaces. So you don't have technicians or operators forgetting the location of sensor in a large building. When the operator is changed, often this information is not passed on, and we have seen cases where the operator doesn't know where the sensor is placed. So these kind of issues can be taken out, and best practice could be sensorless control practice. Now, talking about constant flow applications, traditionally we used to have the duty point selected for a fixed impeller. You will have the flow and head selected. The x-axis is flow, y is head, and the dot is where you have selected, and that dotted line is the impeller line. So you're supposed to operate here, and anything changes in the system, for example, it's operating on a lower head, it would be pumping more flow and it will overload the motor. So traditionally we would install a throttling valve and create head and throttle the pump back into the curve to the design point. This is to ensure pumps reliability over years of operation. So it should operate in the right best efficiency area, and it should also not consume higher power and overload the motor or run into the bearing issues in the pump. But the throttling valve is an investment, and by throttling, we are also wasting energy because it's creating head which is not required in the system. Now, later on, when we had variable speed drives in place, we used to install variable speed drives and slow it down to the required point, but still it would be operating on towards the lower speed, but on towards the right. So we did not have the actual operating point, or the efficiency of the pump or the reliability of the pump is not known over a period of time, and it tends to fail when we don't see the best operating points and best practices there. Now the most easy but old practice is to trim the impeller, which is also somewhat similar to reducing the speed, but you can't increase the head if you require in the future again. So once it is trimmed, you lose that opportunity of future-proofing that pump for future requirements. Now coming to variable flow systems. Now ASHRAE 90.1 specifies that any pump should have or should consume only 30% energy at 50% flow. That means at part load, it should not spend more than 30% energy. 70% savings to be achieved at part load. Now this is for variable flow systems, and this cannot be achieved if we actually practice the traditional way of selecting the pumps. That takes us to the selecting the pumps to the specific application. Now when we have the constant flow pump on the left hand side, so we are used to selecting the pump closest to the best efficiency point, preferably slightly left hand side of the BEP point. So even if the system head is less, then it comes out there and operates and falls into the best efficiency area. This is still a good practice when there's no variable speed drive on it, and you know that you're slightly oversizing the pump head, which is the case most of the time. We all tend to have at least 15% safety calculation on head, and often we all end up providing at least 20 to 25% safety on head, and when the pump reaches site, it's really operating right hand side of the curve. And to do that, we to safeguard the pump and the motor, we select a non-overloading motor. So in this example, you could have selected a 30 HP motor, which is here, the motor curve. So it cuts the impeller curve here, and your duty point is only here. But since you don't have a variable speed control on that, you can't limit the power, and that's why we go for a 40 HP motor, which is a non-overloading motor, and we select a probably 40 HP drive if it comes to the future requirement. Now you end up sizing with a 40 HP motor and a 40 HP starter for a panel for this. Whereas if you still had a variable speed pump on this particular application, you could have selected a 30 HP motor, and you could have programmed not to load the motor more than 30 HP. Now you don't need 1250 GPM as the design flow. You don't need more than that, probably 5% extra, but more than that is still a waste of energy. And it's not good for the heat transfer of the larger piece of equipment. Now, if you have a variable speed controller on that pump, even on a constant flow, it will still reduce the motor size and the starter panel size, and it will still result in a lower installation cost and energy savings. Coming to variable flow, we all know HVAC is a part load industry. Chillers are being selected for IPLVs and part load weightages, but often pumps are selected the same traditional way that we select a constant flow pump. That's like left hand side what we're showing here. So we want an 80% efficient pump, and when we actually put that pump into operation, it's not operating at that particular point for a variable flow system. So let's look at how it operates. So this is a variable flow comparison. Left hand side, a pump selected traditionally to be more efficient at duty point, 80%, and when it unloads to the part load point where ASHRAE specifies 70% savings, you would see you're dropping on efficiency. You're only 68% efficient at that part load condition, where the pump spends most of the time or most of its life. Now, if you spend so much time there, or it doesn't make sense to select a pump this way, but you should be selecting the pump to be more efficient in the BEP best efficiency position at part load. So in this case, we are selecting the pump to be on the right hand side of BEP at full duty point, and then when we slow it down, we falling into the best efficiency point, and because of that, the part load efficiencies are higher compared to the left hand side way of selecting, and it not only achieves ASHRAE 90.1 requirements but exceeds that requirement. So it gives you 77% energy savings in this example. So it makes sense to select variable speed pumps differently, especially when it comes to secondary or variable primary applications. They all tend to operate 24 hours a day, and in our region, and that's why it saves a lot of energy just by selecting it differently. Now, coming to the control of variable speed pumps. So you have 3 different control curve opportunities. The most energy saving option, or the best practice, is a quadratic control curve that connects the design point and the set point, the minimum head to be maintained in a system. Now this is, as we saw, if you put a remote DP sensor, properly set it, probably we will achieve this control curve. And if you have a BMS or a third-party controller that's actually taking control of pumps, usually they tend to connect the 2 dots by a straight line, which becomes a proportional pressure control. It's easy to program, and hence we have seen many places the pumps have been programmed to operate on a proportional pressure control curve. Now, what happens in this is we lose significant amount of energy savings that would have been achieved with that type of control. Now, the other very rare, but there has been cases where we have seen constant pressure set control curves, but it's also equivalent to the sensor placed in mechanical plant room. So we have seen it'll be flat or close to flat. So that's the third type of curve. Now, if you actually compare the energy consumption on all three control strategies, we will baseline the quadratic pressure control curve as the best practice, and we will look at the energy consumption of the other two control strategies. The proportional pressure control curve would still consume 20% more. And if you have a constant pressure control or pump room mechanical sensor, you often see at least 100% more energy consumption compared to the best practice. Now, this is an example worked out, 5,200 hours and 10 cents a kilowatt hour. Now, if you actually see the dollar savings, and if you look at the size of the pump, it's just 10 HP. So if you have a bigger pump in place, and if you look at proper control strategy implemented day one, it would be saving so much energy that it will pay for itself under 2 years. Now, talking about parallel or multiple pumps and redundancy. So traditionally, we used to select pumps to be duty standby, which means 100% duty, and if the first pump fails, the second pump starts, and that's delivering 100% requirement, flow requirement. But if you see redundancy, if you talk about redundancy for pumps, it's slightly different from other piece of equipment. Unlike other equipment, a pump system's redundancy is not directly determined by the number of pumps. Let's understand this. In parallel, two smaller pumps, each sized for 50% design flow, can reduce capital cost, reduce energy cost, and reduce space footprint. So if you look at the traditional way of installing pumps that we have been practicing for many years, two horizontal pumps, and with inertia bases, flex connectors, variable speed drives on the rack or in the panel, and the DP sensor installed in the pipes and wired back to the controller or variable speed drive. Now, if you look at the footprint of this, the space occupied just not by pumps, but also by the control panel, etc. And the serviceable space required around the pumps. And if you actually look at two integrated vertical inline pumps, the footprint is very, very low for integrated pump like this. So integration is really saving you money, not only on initial cost on pump accessories like inertia base and separate panel arrangement, but it is also saving on space. So probably you may need a smaller pump room or a plant room for the pumps. Now, this is a small comparison of two pumps. If you had 8 or more pumps, the savings achieved from this type of installation is going to be very, very significant. Now, that doesn't stop there. You can still go for footprint optimization. There are twin or dual arm pumps available in the industry that has a casing with a single inlet and single outlet port and 2 rotating assemblies. That means 2 motors, 2 impellers, and 2 casing profiles here. So you only need 1 set of valves, and plus you get all the benefits of what we talked about in the previous optimization, like reducing all those accessories and space. Now integration it doesn't stop here. Let's talk about the sizing of the pumps. So 100% flow, 100% duty standby, 20 HP running, 20 HP standby, needs a 20 HP drive, variable speed drive. And if you look at 50% flow rate or capacity, you only need 10 HP each. So that further reduces initial cost of the project. Now, if you take a look at all of the aspects that we talked about, weight, 83% less, installation footprint, 82% less, and installation cost is about 65% less. Now, if you have this kind of opportunity, again, I say this, it's a holistic approach. We have talked about selecting the pump. We have talked about proper redundancies, which I will go into details now. If you have such a holistic approach of smartly using the pumps, smartly using the smart pumps, then you have bigger opportunities than all of us think. So when designing for parallel systems, let's look at this two pump system curve. You have the thick red curve, which is a two pump curve, and that's the 100% design flow. It's a common knowledge that when pumps are selected in parallel, it has to cut the first pump curve so that it falls into the system curve. So the blue line is the system curve, or the system natural resistance, balanced resistance. Now, when the first pump fails, the second pump should still work and deliver required flow in the system. Now, what it does to the redundancy is, okay, so before we go into the redundancy, let's talk about turn down. Most of the installation today is oversized with more redundancy, and when there is low occupancy or low, let's say, oversizing of pumps, you can't reduce the pump speed less than 30% most of the time in today's buildings. Now that's a challenge because it takes us to delta T syndrome and other issues that affects the system performance, just not the pumps. So when it comes to turn down, if you have multiple small pumps, you could turn down the second pump and then completely, and then going to the first pump, you can still go on lower flow rates because you have a small pump. Now it's a 8:1 turn down ratio, and you can approximately operate 12% of design flow, which is solving most of today's delta T syndrome and also saving additional energy to the building. Now, if you have small pumps, you can turn down much lower, and you could still have redundancy. So what is redundancy? Redundancy is a percentage of system design flow available when one operating pump fails. So if you have flow rate at N, then N-1 by design flow gives redundancy percentage. So let's see what kind of redundancies 50% capacity pump can provide. So if you have one pump operating, the second pump failed, the gray line is the second pump's or two pumps curve. When one pump fails, we go into the red curve, and the first pump is operating at that point, and often we have opportunities to slightly speed up the pump to higher RPM and deliver a little more flow rate. So it still delivers, although selected for 50%, it still delivers in a system up to 70% flow rate, design flow rate. Now, these are different combinations: capacity split, 2 into 50%, 2 into 70%, and 2 into 100%. And flow redundancies available when the second pump fails is 70% in the first case, 85% in the second one, and 100% in the third, which is our current practice. Now, if you look at the heat transfer to the cooling coils in the building, which is what is vital to a building operation. Now, even if you provide 70% flow, most of buildings can achieve 90% cooling effect. Now, this is the peak load that we're talking about, which is less than 2% of annual operating hours, or most buildings don't see that peak load at all, because we have designed with enough care and redundancy on not only the pumps, but the other equipment as well, even the cooling coils. So if you take the second case, 70% split, you will have 95% cooling capacity even when the second pump fails. So this meets the peak demand for the building in the worst of scenario. Now, if you can get 95% cooling, look at why we should size 2 into 100% capacity of pumps, or 100% redundancy. So that takes us to why we should select. So there are different applications: generic duty, high comfort sensitivity, and more mission critical applications. So if you talk about generic duty, 70% flow redundancy is more than enough. Type of buildings include schools, apartments, condos, factories, and warehouses. Now, if you come to high comfort sensitivity applications like hotels, offices, commercial and mixed use outpatient clinics, and universities, 85% flow redundancy will still cover the sensitivity or requirement of that application. Mission critical, of course, requires 100% standby, and we still select 100% redundancy for critical care facilities like blood banks, data centers, and hospitals. So type of pump staging. Now, speed-based staging is very common today. 98%. It's popular in the region. There is a BMS controls contractor or plant manager that takes staging controls of the pumps. And once the first pump is loaded to, let's say, 90%, it starts the second pump. That's the speed-based staging. Flow-based staging is more efficient, best practice, but it needs a flow meter, which is expensive to have it in the each line or each pump, or if you have it in the main header, then you will need a bigger flow meter, and it becomes more expensive as well. So often we don't see this flow-based staging due to this challenge, but smart pumps can provide flow from their controller. So this is another opportunity that you might have going by flow-based staging. Best efficiency staging is what we want to see in the industry. It's the best of practices. Once we know the hydraulic performance maps of those pumps, and we embed that performance maps in the smart pump controls, they will stage pumps based on best efficiency. Now, this saves up to 30% operating costs just by staging it differently on efficiencies. In summary, cost to install complexity, operating cost, all of these best efficiency staging scores much better compared to flow-based staging and speed-based staging. Now, just let's take a look at comparison of how a speed-based staging versus a best efficiency staging works. So here I'm showing a speed-based staging curve at the bottom. On the top, you have best efficiency staging, and this is 3 pumps curve. This is 2 pumps together, one pump curve. And if you go up on the efficiency scale, you are much better. And this is number of pumps working. Green is working, red is stopped, and power consumed. Now let's look at what happens when the first pump starts in both cases. So the first pump starts. In both cases, up to this point, there is no change. Both are same. But when it reaches this point, the best efficiency staging knows that it's dropping in efficiency scale. This is efficiency scale, and if you load the pump further, you're dropping in efficiency scale. And that is going to consume more power versus in the best efficiency, you have the opportunity to stage the second pump and operate 2 pumps at low speed. So let's see what happens from this point. So the speed-based staging has loaded up the first pump to approximately 90% speed, and the first best efficiency staging has staged on 2 pumps, operating 2 pumps at part load, but on high efficiency point. Now, although it's operating 2 pumps, the power consumed is less than 1 pump operating at full speed. This is one opportunity point. Let's plot that point here. Now, the second pump to third pump transition, also same opportunity exists. And if you actually look at that operating point and put a load profile on the same curve, you will see you're spending most of the time at that point for this load profile and this point as well. So if you put a 3 into 40 HP pumps and a dollar value for that savings, it is coming up to 34% energy savings just by staging pumps on parallel and best efficiency points. So in summary, if you connect pumps to cloud for optimization and sustained performance, you get the most of the performance of the asset. Use sensorless to avoid higher installation costs and the risk associated with the sensorless systems. By knowing the flow rate, we can achieve more energy savings, not only for the pumps, but also for the system as a whole. And quadratic pressure control curve saves higher energy and gives more value for money over a period of time. And this holistic approach reduces the capital and operating cost by following all of these best practices. So consider appropriate flow redundancy, 50% or 70% split to reduce your operating costs. Consider best efficiency staging in parallel, which will save up to 34% energy savings while operating on part load conditions. With that, I pass it on to the panel for questions.
Thank you very much, Mr. Raja Mohan. I'm Yunus speaking. Yeah, I'm the treasurer for the Ashre Bahrain chapter, and I thank you all audience that they came here and they joined this webinar. And I really thank you very much, Mr. Raja Mohan, for providing such an useful information to us about energy saving in pumping system, just by changing the selection point of view. Okay, it was really worth listening to you, and I would like to say thanks on behalf of our attendee as well. Now I'm going to take all the questions in our systems, okay, which have came to us. There are so many questions, but as our time permits, very small time is permits to us. So we will try to take as much as we can. Okay, the rest question will be answered through the email. Okay, so one Mr. Nixon has asked, one Mr. Narendra Pal has asked that this, as you told, I will try to start from this. They are asking that what should be the pump capacity that is based on total low side flow requirement or diversified load requirements. So they are asking simply that how much pump capacity, as you explained, that we should take for different buildings, we should take different compositions as per the requirements. So they just want to elaborate on that.
Okay, so I'll go back to that slide. So based on the applications, the generic duty, you should have, it's good to have 2 into 50% split. You still have 70% flow redundancy, and you have 90% heat transfer capacity to the building. And if you take the next level, which is a 2 into 70% flow split for the pumps, you still have 80% flow redundancy, and that gives 95% cooling transfer capacity. And finally, the 100% for mission critical. So based on the building requirements, not only the flow, but we should look at the heat transfer. So if you can get 90%, and if the building doesn't need more than 90% cooling, then you could go for 2 into 50% split. If it needs slightly more, 95%, then you can go to the 2 into 70% split capacity.
Yeah, thank you very much. The other question is from Nixon. Mr. Nixon, he want to ask that as you told that there is no DPT will be installed at in the chilled water pipelining for ramp up and ramp down the VFD. So he just wanted to know that if there is a pressure drop, if there is a pressure drop in chilled water pumping and VFD need to ramp up, then instead of analog, how the system will sense about the pressure and the current in this system?
Okay, so the smart pumps today have the performance map of the pump embedded in the controller itself. So if you see the performance maps are in the pump, so it knows where it is operating, number one. Number two, it's a closed loop circuit, and any pressure change or flow change in the system, according to the simple affinity law of a pump, should change the amperage of the pump. Now, if the system conditions are changing, either the flow or head or both, then amperage is changing, and by sensing that amperage is changing and looking at the performance map, the smart pumps can sense the demand of the building, and as per the demand, they can slow down. So when we say no sensor or sensorless, the inbuilt sensors are made use of with the program maps and intelligence built in.
Thank you. One more question is from Mr. Rajesh. Actually, our audience is having so many questions. He wants to know that how smart pumps are connected to BMS and what is the protocol about that?
Okay, smart pumps can always provide all the information or the connectivity that you traditionally used to have. Let it be hardwiring or a BACnet or a Modbus protocol. So that's available as default. So you don't have to think about a smart pump as an alien. But in addition to that, smart pumps also can connect to cloud by Wi-Fi, which means today we are bridging cloud to cloud for better connectivity and information flow, diagnosis, preemptive maintenance, and all that. So machine learning is implemented, and the pumps connect to cloud, and that cloud is connecting to the asset management platform of a customer. So he can sit in a centralized monitoring platform, and he can still view the insights of the pump. So simply put, smart pumps provide additional insights, just not the information that you would get from BACnet or a Modbus protocol. That is just data or information. But insights can be provided by cloud-based connection and machine learning. Hope that answers the question. Hello?
Yunus, unmuted.
Oh, thank you. Thank you, Pankaj. Yeah, actually, there are a lot of questions in the series. Okay, but as the time doesn't permit to us, so I will try to take one or two more questions to you. Okay, so there is one question from Mr. Ronak Anjum. He just wanted to know that is there any sensorless chilled water system installed in Bahrain somewhere, anywhere?
Yes, there are a few. We can just drop a note to me. There is my email ID on the last slide, so references can be given, and we can visit site to see how it's working.
Okay, thank you. Actually, there are one more questions I would like to ask. And I think after that, it will go to our President-elect, Mr. Farhan, for vote of thanks. So the question is that when we are having more than one pump working in parallel, how the selection of pump or performance will affect? Will there be higher capacity of motor for parallel pumping, or same motor will work? Although you have answered this in the slides, but I think the audience wants to know more about this.
Yeah, so let me go to the slide quickly. Yeah, so when you actually select parallel pumps, the second pump is failing, so you will see the first pump curve is coming to the end and it's cutting the system curve. So when it comes to this position, this you will know this particular point of operation, what power it needs, and the motor should be sized appropriately so the motor is not overloaded. So that's how we size it, looking at the pump curves and where it intersects the system curve and appropriately sizing the motor.
Okay, thank you very much. Yeah, although it was my last question, I was thinking that it is last question I will ask, but the persons are asking more and more questions. So anyway,
okay.
If you allow, I will ask to take one more questions now.
Sure.
Yeah, actually, some people are asking that from the service point of view, okay, like we have to replace the motor and VFD. So they just wanted to know that as the system is integrated system, so they do have to approach the manufacturer only, or they can do it locally as well if they want to change the motors, etc. Motor or VFD.
Yeah, there are certain cases where you will have, let's say, a particular manufacturer offering the whole motor and the controller together. But most cases, you will have hardware, there'll be a variable speed supplier, variable speed drive supplier who supplies to a manufacturer, and you will have the hardwares available locally. And when it comes to actually smart pumps, you should all be confident that a manufacturer who is very sound and has better technology is implementing this in the industry based on a lot of R&D. So it's not now variable speed drives are reliable than much more than it was 20 years ago. So it's even more reliable than a contactor or a switchgear arrangement. So this is how we have to look forward. And if to directly answer that question, if you want to replace a motor is a industry standard motor in most cases. So induction motor is a standard frame size. You can replace the motor, you can service the motor locally. There's no problems most of the time. But yeah, and variable speed drives as well. Most of the time it's available. What you will be missing here is once the controller fails, the program, if you don't buy from the manufacturer, is not copied over or reprogrammed on that controller. So if you don't use that program again on that controller, you miss the whole opportunity of that energy savings potential. So,
thank you very much. Thank you very much. And this is the last question for today's evening. That Mr. Prajesh Kumar want to know that for sensorless technology, the pumps is having inbuilt sensor or something, the speed variation based upon ampere or voltage variation, will it be efficient compared to through sensor? Like suppose the sensor-like technology pump are having inbuilt sensors. So is it better or the speed variation based upon the amperage or voltage is better? Which one is better?
Amperage or kilowatt based staging is better two ways. One, the last sensor to fail in the industry, you take chillers, pumps, cooling tower fans, whatever equipment. But if the amperage sensor fails, the equipment is down. Now, that is very specific to variable speed drive. So if the drive fails, the total system is going to be down. So that's the last sensor to fail, number one. Second, it doesn't need calibration over time. Amperage sensors are more reliable and doesn't drift over time. But to add to that, it's not only on the amperage, but also on the speed and amperage and the embedded performance maps that we have inbuilt. So it's just not by another PID loop or amperage. It's a smart logic that is built in, and definitely I can confidently say that it's much better than the field sensors.
Okay. Thank you very much, Mr. Raja Mohan. That was all for tonight evening. Okay, now I will request Mr. Farhan to come and provide the vote of thanks. Yeah, over to you, Mr. Farhan.
I just wanted to welcome Mr. Richie, who is joining with us today. Thank you, Mr. Richie, and thanks for encouraging us. Mr. Farhan will introduce Mr. Richie and invite him for a few words.
Thank you. Farhan, I think you're muted.
Yes, still we cannot hear you.
Hello, good evening. Good evening. Sorry for interruption. And it's a pleasant surprise for Bahrain viewers that it matches with the theme of our X-ray this year's, that digitalization. And because of that, we could have our a very prominent personality of HVAC industry, Mr. Richie Mittal, along with us. And it's really an honor to share a screen with you, sir. Mr. Richie is a very prominent in HVAC field for 35 years of experience, and I had some talk with my younger brother who is in India. And when I mentioned his name, he was just, very happy that, oh, Mr. Richie is on the panel. He said, oh, he knows very well Mr. Richie. Mr. Richie is involved in energy efficiency field for a lot of years, in renewable energy also, and he is in ASHRAE associated with the RAL region at large as regional membership council representative. And I will not take much of a time because I want to hear him more. So I will just give space to him. So please come and say a few words of encouragement for us. Thank you.
Thank you, Farhan, and thank you, Pankaj. It's really great to see Bahrain in action, I would say. And you rightly said, Farhan, that because of virtual world, we are able to meet each other. And I can see Adil also here. We are in touch with each other, and because of this virtual platform, it's a time to learn from this virtual. I think that's a way forward, and I think all the webinars, whichever any region, any chapter which is doing. And most of the members, and it's excellent. I would say, Rajmohan, you did an excellent presentation on Armstrong. I'm using Armstrong, so I know the product quite well, and I know the efficiency of the product also. So it was a very well presented thing, and I'm glad to see Bahrain in action, and look forward to having you more and more on seeing you virtually. I don't know when we are going to see face to face, but we are looking at CRC in December, which may not be face to face as of now in South Africa. But till then, I think we keep on seeing virtually. And thank you for whatever you're doing for ASHRAE. Thank you very much.
Thank you, sir. Thank you very much.
Thank you.
Mr. Adil, would you like to add some words?
No, I was just wanted to thank Mr. Richie that he was a very good surprise that he was here and he encouraged us. He might be seeing us for a couple of years. And since we formed the chapter here in Bahrain and how we ups and downs that happened here in Bahrain.
Yeah, me and he were there in Jordan CRC. We met there, and then we can realize that the dedication of the team there. So that has really encouraged us to
let's hope for face-to-face meeting in Cape Town.
Here we will put all our maximum effort and see that we do our best.
Now we come to a point where I have to deliver the vote of thanks, and it gives me immense pleasure to deliver the vote of thanks for this wonderful evening. It was a standing lecture by our eminent guest on the topic smart pumping for maximum efficiency and cost saving. I'm sure everyone has gained valuable knowledge. A big thank to our guest speaker, Mr. Rajmohan. This was our first webinar in this society year under presidency of Mr. Pankaj Amin. So a hearty thanks for our new president of ASHRAE Bahrain chapter, and we wish him a rewarding year ahead. This wonderful event became possible due to tireless effort of our digital team consisting of Mr. Yunus and Mr. Vinod. And I can say with certainty that everyone enjoyed it, so a deserving thanks for both of them. Finance is the backbone of all events. We are fortunate to have sponsors who always stood by us. And I take this opportunity to thank our sponsors, BTA and Armstrong, whose valuable contribution made this event possible and successful. We have a series of events lined up for this society year, and we wish to see you all again. The next event is on 28th of this month, which we are organizing jointly with Rajasthan chapter. We shall be sharing the details of registration by tomorrow. Last but not the least, a big thanks to all of you for joining in great numbers and making this event outstanding. Please do not forget to give your valuable feedback so that we can improve upon our upcoming events. With this, we conclude the webinar. ASHRAE Bahrain team thanks to all of you again. Enjoy your evening and good night.
Good night. Thank you. Thank you, Mr. Richie.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you. All the very best.
Thank
Thank
you.
you so much.
Thank you.
Thank you. Bye. Bye.
Thank you, Mr. Rajmohan.
Thank you. Thanks everyone.
Thank you. Thank you.
Mr. Raj,
Thank
see you
you,
again.
everyone.